This podcast is sponsored by Lightstep. Lightstep delivers confidence at scale for those who develop, operate, and rely upon today's powerful software applications. Answer questions and diagnose 100% of anomalies, spanning mobile, monoliths, and microservices across every service in real time. Visit lightstep.com.
The promise of Java has always been write once, run anywhere. Designed with the just-in-time compiler C2, Java applications allow developers the ability to write applications and target a platform during just-in-time compilation. That flexibility has often given rise to comments like Java's slow. What if you can compile Java to native code? Hi, my name is Wes Rice. I'm the host of the podcast. Today on the podcast, we're talking to Thomas Wuerthinger. Thomas is a senior research director at Oracle Labs, leading programming language implementation teams for languages including Java, JavaScript, Ruby, and R. He is the architect of the Graal compiler and the Truffle self-optimizing runtime. Previously, he worked on Crankshaft optimizing compiler of V8 at Google and the Maxine Research Virtual Machine at Sun Microsystems. He received his PhD from JKU Linz for his research about dynamic code evolution. Today on the podcast, we'll touch briefly on GraalVM, but more quickly move into a discussion of just-in-time versus ahead-of-time compilation on GraalVM. For a more detailed discussion on GraalVM, including Truffle, its multi-language support, and its JavaScript context, check out the podcast or talk from Duncan McGregor on InfoQ.com and QCon London. Thomas, welcome to the podcast.
Hi.
So GraalVM was initially thought of, I guess, when it came out as a replacement for the JVM C2 just-in-time compiler. That project scope has changed since it was first released. Can you talk a bit about its history and kind of current scope?
Yeah. So initially we thought, well, let's just replace the current C2 just-in-time compiler in Hotspot with a compiler that's written in Java and that's written in a modern object-oriented design. That was the original project goal. But since then, a lot of things have changed and the project scope has increased quite a bit. One of the things that increased is the kind of languages that we're targeting. So we are not just targeting Java as a language, but also JavaScript, Python, Ruby, and R as dynamic languages. And the other thing that has changed is that we developed not just a just-in-time compiled mode of running GraalVM, but also an ahead-of-time compiled mode. And I mean, all of this is actually kind of a testimony for one of the advantages of writing the whole system in Java, which is that it is a very modular design system that allows us to target many different ways of how to use the core components of the compiler.
So we actually have another podcast, again, I mentioned with Duncan McGregor, that talks a bit about Truffle and talks a bit about how you target other languages. But just briefly, how is it that you're able to target things like Python, like R, and JVM languages?
What we do there is we use a technique called partial evaluation of interpreters. So write an interpreter for your dynamic language in Java, and then the compiler is able to partially evaluate that interpreter and produce optimal machine code for it. This is a new research technique that allows us to add additional languages, domain-specific languages or dynamic languages to the GraalVM system without a lot of additional effort.
And when you do that, how is the comparison between a language implemented for GraalVM versus its traditional normal approach?
That varies highly from language. For some of the languages that have a lot of industry investment, like JavaScript, we are roughly at the same speed. So our performance is approximately comparable with the V8 JavaScript engine, for example. For some other languages that have less industry investment in terms of just-in-time compilation technology, like Ruby or R, we have scenarios where we are much faster because of the server-side just-in-time compilation that we apply to those languages.
One question that kind of begs is why? Why would you want to do that? Why would you run R on the JVM rather than natively?
One is performance. At the moment, a lot of R programmers are forced to rewrite hot parts of the code in C or C++ for maxing out performance. And here you can avoid that. Another thing is that you have a nice interoperability with your JVM. So you can, from your Java program, directly call R statistical functions without doing inter-process communication or other complex setups.
Makes total sense with something like R, which is kind of often hard to scale. But what about like Rust? Why Rust on the JVM?
So Rust or other native languages they would typically interact with JVM-based languages via GNI, but GNI has quite some overhead. So when you go back and forth between C, C++, Rust, or Java, then you will find that there is quite a lot of overhead on the GNI boundary. And what we can do with GraalVM is to completely remove that GNI boundary and compile the Rust, C, or C++ code and the Java code into the same machine code.
Let's jump in and start talking a bit about that. At QCon New York, you did a talk about just-in-time compilation versus ahead-of-time compilation. I'd like to spend some time pretty much talking about that for the rest of the podcast. What is ahead-of-time compilation on the GraalVM?
So GraalVM has a way that takes a JVM-based application and then does a so-called closed world analysis, where we figure out all the code that is reachable from the application's entry point. And once we've done that, we subsequently create ahead-of-time compiled machine code from that, like a binary that can run on its own without the need for a Java virtual machine being present.
Okay, but what about things like reflection, things that you don't necessarily have visibility to ahead of time when you need to compile?
So there are some forms of reflection that we automatically detect and correctly kind of anticipate when we do our closed world analysis. There are some more complex forms of reflection that require some manual configuration at the image generation time. The reason for that is that if we allow arbitrary reflection, it is kind of not possible to create a closed world around your application, or at least the closed world would be very big, meaning like everything would become reachable. And one of the goals of the ahead-of-time compilation here is to create a small binary and to create an efficient machine code. And therefore, we need to have a constraint on what is reachable.
And so this creates a compiled native binary for a target platform?
Yes, you need to select the target platform ahead of time. That includes the operating system and the ISA. The other thing is that this binary has a garbage collector inside. So it still has some runtime system in it, but it does no longer contain a just-in-time compiler and also no interpreter. So all of the machine code is already compiled when the binary is created.
What type of flexibility do you have with garbage collectors? Can you still pick G1, GC? Can you still switch things around? How does that work?
So at the moment, we have only one single default garbage collector when you create that native image. So you cannot select all of the garbage collectors in Hotspot. But we are currently working on removing that limitation and adding support for low latency garbage collectors as well.
What are we seeing when you create one of these, targeted binaries? What does it look like in as far as size and the package itself?
Yeah, so the only thing you need when to run the application is that one file, which is the binary. That binary can have somewhere between 6 megabyte or also maybe 50 megabyte or something like that. But depending on how much code ends up in that binary. But then when you run that, you do no longer need any Java virtual machine or Java libraries. You only need that single binary.
So no more class path?
No class path, nothing. And the other thing to add is that you can statically link system libraries with a -- static flag when you create that native binary. And in that case, you can run that native binary on a bare metal Docker image. So you don't even need a Linux distribution or anything like that as your base image when you run that on Docker.
As of 19.0, and I think it's 19.1 now, it's production, right? So this is a production system.
Yes.
Okay, and then it targets OpenJDK 8, is that right?
Yes, we're currently based on OpenJDK 8.
So why 8? Why not 9? And what's the path for moving forward with 11?
So we are actively working on 11 support. It's one of our top priority items to make the system also available for JDK 11. We are on 8 mainly because when we started the process of kind of getting more stable towards the release, 8 was still the last long-term support release. So for historical reasons, we're still on 8 here, but we are actively working on 11 at the moment.
As we were talking before, I should have mentioned more about some of the use cases that you're seeing. What are you seeing for adoption with Graal? Are you seeing this on embedded devices? Are you seeing this on edge devices? Are you seeing it on mobile? Is it server-side Lambda type environment? What's the adoption of Graal?
There's many different scenarios where people use Graal. I think the main adoption in production at the moment is for server-side applications that would run in the just-in-time compiled mode, but that would use the additional performance benefits from the GraalVM Enterprise compiler. So I think this is one of the areas where we see main benefits. The other thing that's actually running on production for some time now is the Twitter workload, which is also a server-side JVM-based workload, where the GraalVM compiler helps with additional throughput, and it also helps with reducing the garbage collection pressure in the application. So this is kind of one area.
So Twitter's running GraalVM today?
Yes, Twitter is running GraalVM today in production. It is running with the GraalVM compiler enabled for their services.
Very nice. And that's like on the hot path, the main path for all of their microservices?
Yes, Chris Tallinger gives a lot of talks about the benefits they have from using the GraalVM compiler.
One of the things, as I mentioned in the introduction, that Graal introduced is kind of as the scope changed, is this idea of ahead of time compilation. Why the need for ahead of time compilation?
So just-in-time compilation has a couple of drawbacks versus ahead-of-time compilation. And the main one is startup time. The reason is that if you do just-in-time compilation, there's a long time at the beginning of the application where the application is not running with the best machine code. And that is because first you start interpreting, but actually first you even load the bytecodes, you verify the bytecodes, you run the bytecodes in the interpreter, you gather some profiling feedback while the program is running, which has also an overhead. And then you create kind of your first tier compilation, usually with a faster compiler like C1. And then only after the method is run for thousands of times, you would finally attempt to create the best possible compilation for that method. And only when that compilation finishes and the machine code is installed in the system, you run at your maximum peak throughput for that method. So there's a long sequence here that is contributing to the startup issues with just-in-time compilation. And in ahead-of-time compilation, you have the ability to do all of this sequence only once when you deploy your application and not do it every time you start it. So that's one of the benefits. But startup time is not all of the benefits. The other thing is around, for example, memory footprint. And here, the reason is that in a just-in-time compiled system, you need a lot of metadata that is adding to the overall memory footprint of the JVM process. So this is metadata about the code that is loaded, the names of methods, the names of local variables for debugging. You need the whole program that is loaded in some way as a data structure in memory. And the other thing you have in there is you have profiling data that is also kept in memory. So that means you also have on just-in-time compilation a memory disadvantage. So these are, I think, the two main things why ahead-of-time compilation can be beneficial here. There are some minor benefits as well around the ability to do better global optimizations that would span across certain methods, because a just-in-time compiler usually only looks at a certain method.
The promise of Java has always been write once, run anywhere. With ahead of time compilation, are we giving up on that? Are we saying that we know enough about how our machines are going to run in production that we can specify the processor at design time and give up on the just-in-time compilation need?
So the benefits of just-in-time compilation is the ability that when you deploy the code, you don't need to know which platform it will run on. With ahead-of-time compilation, you could still have something where when you are distributing the code, you would distribute the platform-independent parts, and you would do the ahead-of-time compilation potentially just at the latest possible point when you finally know your platform, right? So you can, with ahead-of-time compilation, also have something where you, for example, do the ahead-of-time compilation only once you deploy into the cloud, into a certain cloud instance, and you know the type of ISA and operating system that runs on that cloud instance. So I think nowadays, in many scenarios, you will know at some point before you run that application at scale, you will know I will scale on this specific processor instances and I will know this specific target platform. So I think in nowadays environment, it is not that important to kind of keep that platform independence. Also, you could still do that in the sense that it is your choice at what point you go platform dependent, right? Even with the head of time compilation of GraalVM, you can still have a platform independent way of distributing your application, and then only later do the head of time compilation that turns that platform independent jar file, for example, into a platform dependent native image.
Makes total sense. So before you were talking a bit about how C1 takes initial pass, C2 kind of optimize it once things have been running for a while. You've got a good plan for how to optimize things. With GraalVM, do you go straight to that kind of optimized plan? Are you going to get better performance with running C2 for a long time? Or does it go straight to kind of getting better performance right off the bat?
So in the GraalVM just-in-time mode, we are only replacing the C2 compiler. And in that setup, it is the exact same sequence, meaning warm up in the interpreter, warm up with C1, and then you go to the GraalVM compiler for just-in-time compilation. So in the just-in-time compiled mode, it's the exact same sequence, just with the C2 compiler being replaced with the GraalVM compiler. In the ahead-of-time compiled mode, we don't use any other compiler. We only use the GraalVM compiler for the final machine code. And so there is no warm-up sequence or anything like that. So one disadvantage of the ahead-of-time compiled mode is that you do not have, by default, information available that tells you about the behavior of the application. So you're missing profiling feedback. Usually a just-in-time compiler would run like the application for some time and then make an educated guess that the way the application is behaving in the first couple minutes will hopefully be kind of the way it will behave moving forward, and do optimizations based on the data it gets from the profiles. In the ahead of time compiled mode, such a profile is not available, so the compiler needs to be more conservative in its optimization, and it doesn't have as much information about how the application behaves. But that is why in the ahead of time compiled mode, there is a way to mitigate that by gathering profiling feedback from a previous run of the whole application. So what GraalVM enables there is like you run a couple tests or benchmarks, and you gather profiling feedback from running that, and then you feed that profiling feedback into your ahead of time compilation process. This can actually be then an advantage of the ahead of time compiler because your profiling feedback might influence the application's performance, and it's much more predictable when you can gather such profiles ahead of time and then fix it for your application. And the other thing you can do there is that if I want a certain part of the application to be fast, I can have my tests and benchmarks that are gathering that profiling feedback be focused on that part of the application. So with profiling feedback gathered ahead of time, you can actually more deterministically make sure a certain part of your app is fast, whereas in the just-in-time compiled mode, the just-in-time compiler will always just try to approximate from the initial startup behavior of the application throughout the whole application run.
So when we talk about performance, there's a lot of ways that we can consider what's performant: memory, latency, throughput. What are some of the measures that you're seeing, and how do you make those trade-offs with GraalVM?
So in the just-in-time compiled mode, we are heavily focused on maximizing the peak throughput. And our goal is there to have a better peak throughput than the C2 compiler. In this mode, we really try to maximize the application's throughput over the longer term. And the other mode that you would run us in the ahead of time compiled mode, here's where we are trying to maximize startup, memory footprint, and packaging size. So those three metrics should be low, meaning startup time should be low, a memory footprint, the total memory occupied by the process should be low, and the packaging size, meaning the final Docker image that is used to run your applications, should be small. So these are the three things you try to optimize in our ahead of time compiled mode. And in the ahead of time compiled mode, we are behind our just-in-time compiled mode in terms of peak throughput. It depends a little bit on the application, or it also depends on whether you do profiling feedback or during the ahead of time compilation process or not. But it can be approximately in the 20 to, if you don't have any profiling feedback, maybe even 50% slower in terms of peak throughput than our just-in-time compiled mode. And in terms of latency, currently we also would have higher max latency in the ahead of time compiled mode because of the more simpler garbage collection algorithms that are available in that execution mode.
Very nice. So you mentioned that you hit production. You're at 19.1 now. What's on the roadmap going forward?
One of the things we're doing is that we are trying to add support for Java 11. I think that's probably our top priority right now. We want to make sure that native image and also the GraalVM compiler works with Java 11 and newer Java versions moving forward. The other thing in terms of platform support that we're working on is to have better support for Windows. We have currently technology preview for Windows, but it is still experimental, and you want to make sure that this gets towards production as well. You mentioned before mobile platforms. We are working together with Gluon to enable mobile platforms. There we have support for ARM 64-bit and to run on iOS. Voyin Jovanovic from the GraalVM team recently gave a talk and demo about that at the Scala Days in Lausanne. So this is regarding our platform support. And then regarding our performance-related work, we are continuously improving the performance of our just-in-time compiler for peak throughput. One of the changes we did there is to have a little bit faster compilation speed as well. That's the major change that came in 19.1, where our GraalVM just-in-time compiler is faster in producing the machine code, which can be very important for less long-running workloads, like workloads that only run like a few minutes. And we are continuously improving that. But then for the native image, the ahead of time compiled mode, our roadmap there is focused around mitigating the drawbacks that we currently have for the ahead of time compiled mode. And this includes the performance drawbacks. One thing is the peak throughput that we want to address by improving kind of the quality of machine code of the final ahead of time compiled binary. And the other thing there is to enable the support for low latency garbage collectors in your native image, such that this is also not a consideration you need to worry about when you run the ahead of time compiled mode.
Speaking of that, what is the cadence and release cycle for GraalVM?
Our target here is to have a release approximately every 3 months. We are numbering those releases where the major number is the year. So we had 19.1, we'll soon have 19.2. And we are planning about 4 of these major releases every year. And the goal here is to have the last release on a year to be release that will have longer term support. So basically the last release on 2019 is going to be a release that will support with backports for a longer period of time, and simultaneously with the 20.0 release. But we want to bring out new features like gradually, and basically make sure that like GraalVM users are always on the latest bits and don't have like big steps where they need to upgrade in a very painful way. And this is why we are on a release schedule that gets out a major release every 3 months.
And what is the relationship between CE and EE versions when you release?
We always release both versions simultaneously. So when there's a new version for CE, there is also a new version for EE.
And what is the compatibility between the two?
They are 100% compatible, meaning every program that runs on EE can also run on CE. that is a very important aspect for us in the project, because we don't want users that start using EE to have any fear of any type of lock-ins. Meaning, if an EE user feels like he doesn't need the support or performance that comes with the Enterprise Edition anymore, that user should be capable of downgrading to the Community Edition without major problems.
Very nice. Well, Thomas, thanks for joining us on the InfoQ podcast.
Thank you, Liz.